This next series of videos will talk about inference for counts and proportions. We'll talk about how we can model events and distributions with the binomial distribution. We'll talk about how we use a normal approximation. We'll talk about how we describe the relationship between population proportions and sample proportions. We'll talk about how to carry out hypothesis tests for counts and proportions. And we'll talk about how to understand the sample size needed for these various tests with counts and proportions. And so we're going to start by talking about the Bernoulli and the binomial distribution. So the Bernoulli distribution is a very unique one. It is a discrete random variable. That is, it has two possible outcomes. So these are very common across life. Think about a coin flip. Think about the status of a tree. That tree might be alive or dead. You might inspect a facility if you're an environmental technician. You're going to inspect a facility and detect whether or not it's compliant with hazardous waste storage. And that's a yes or a no, a binary outcome, as we like to say. And so we'll talk a lot about the binary outcomes and how they relate to the Bernoulli distribution throughout this topic. And so the goal here is that we can make repeated independent trials from a Bernoulli distribution. And all that means is that we can flip a coin several times, or we can go to different trees and continue to mark whether or not they're alive or dead. And so that's an example of a series of independent trials that are repeated. What we might want to know is how many successes do we have, X, that is, how many trees do we encounter that are alive, and what's the proportion of those successes? Maybe 60% of the trees we counted are alive. And we assign a label to each success. Typically in statistics, we'll tag them with a 1 or a 0. The Bernoulli distribution is really one of the most simplest discrete distributions, and it's really the building block for lots of others that we'll talk about later in the class. So here's the mean and the standard deviation of a Bernoulli. It's relatively straightforward. That is, the mean value mu is 1 times the proportion plus 0 times the complement of that proportion. And this actually turns out to be 0. And so the mean value, mu, is p, is the proportion that you're interested in. And so we can calculate the variance. We get to certainly take the square root of this variance to calculate the standard deviation. We take the variance as 1 minus mu squared times p, and then we add to that 0 minus mu squared times 1 minus p. And when we do all the algebra out, we get the variance equal to p times 1 minus p. And so the value, you can think about it as in this table, the probability p is when the value is 1, say our tree is alive. The probability 1 minus p is 0, say when our tree is dead. And so we might be able to look at the mean and standard deviation of the Bernoulli through this process. There's a short mnemonic that tries to look at the Bernoulli trials and how they come to form a binomial distribution. And I want you to think of the numbers or the letters BINS, B-I-N-S. So if it's binary, that is, each trial can be classified as success or failure. If it's independent, the trials must be independent of one another. That is, knowing the result of one trial doesn't have any effect on the result of the next trial. So every time we flip a coin, whether or not we get a heads or tail this round, it doesn't matter what we got in the last round. This is an independent trial that's not influenced by the previous trial. The number is the number of trials n that some chance process must be fixed in advance. Say we're going to flip a coin 10 times. N will be 10 in that case. And then we might know the success. On each trial, the probability p of success must be the same. That is to say, the probability has to be constant. If we're using a fair coin, the probability of getting a heads needs to be 0.5. So I want you to think about and remember BINS as a reminder of these conditions when we start to talk about the binomial distribution. So more about that binomial distribution. We can think about the binomial distribution as the proportion p of successes in some population. And so we can say that the binomial distribution has two parameters, n and p. where n is the number of observations or trials, and p is the proportion. And so the graph here shows a binomial distribution with n equals to 15 and a probability equal to 0.2. All of the possible values of x are the whole numbers from 0 to n. That is to say, we need to have some whole number. We can't have any values with decimals. That would make it a continuous distribution, but the binomial, again, remember, is a discrete distribution. And so we might want to find out the form of the binomial distribution. And this is a formula we can use to find out the probability that certain things happen, given we know what n and p are. So n is our number of trials, p is our probability of success. The probability of exactly x successes can be found with this formula. That is, the probability that our uppercase letter x, our random variable x, is equal to some value x. So the probability that I get 2 heads of a coin when I flip it 5 times, I can calculate that. Little x would be 2. So we can find this out by n factorial and exclamation point. Some people will ask, why are you so emphatic about your numbers and letters in this formula? Well, n factorial simply means we take each value, x times x minus 1 times x minus 2, all the way down to 1. And so n factorial divided by x factorial times n minus x factorial. And then we take our proportion p raised to the x, and then 1 minus p raised to the n minus x. And now we can find the probability of successes for a specific x number of values. And so just like with other discrete distributions, we can calculate these values that correspond to some event occurring for the binomial distribution. The mean and the variance of a binomial, this is going to be important as we think about how do we characterize the binomial distribution. Well, let's call this mu sub x would be the mean of the binomial distribution. And all you're doing is you're running a series of trials and you have a probability p of each success. Well, then you can just multiply p by n, and that will be your mean value. So n times p is equal to the mean of the binomial. The variance of the binomial, same thing. We basically take the proportion times 1 minus the proportion, and then we add to that n number of times that we're running our trials. And so then the variance would be n times p times 1 minus p. And so this is going to be important when we think about how we characterize the attributes of a binomial distribution. We're going to go into some calculations for how to do this using this example. The first one asks for 2 different questions. So again, let's go back to the hazardous waste example. You're an environmental technician. Your job is to inspect facilities and to make sure that they're compliant with how they store hazardous waste. So let's say in a day, you can inspect 8 facilities for hazardous waste compliance, and there's a probability p equal to 0.24 that they will be issued a violation. And so we want to know 2 questions. What is the probability that exactly 2 facilities will be issued a violation? And then what about the probability that 2 or fewer facilities will be issued a violation? And so in the latter case, we're going to be interested in not only what is the probability of 2 facilities issued a violation, but the probability of 1 facility issued a violation, and the probability that 0 facilities are issued a violation. And so we'll go through some calculations that determine that. And then our second calculation will be looking at the mean and the standard deviation for the hazardous waste example. You'll recall that we inspected 8 facilities for hazardous waste compliance, and there's a probability p equal to 0.24 that they will be issued a violation.